Imagine standing in the batter's box, your heart pounding like a war drum, eyes locked on the pitcher who stares back with cold precision. He winds up, releases the ball, and for a moment, it looks like it's coming straight at you. But then, like something out of a magician's act, the ball veers sharply to the side, leaving your bat slicing through empty air. You've just witnessed one of the most deceptive phenomena in sports, the curveball. But what if I told you that this isn't just athletic skill or sleight of hand? That what you just saw is the result of physics so intricate, so bizarre, that it actually fooled scientists for decades? That behind that graceful arc is a world of spinning air, invisible forces, and the very limits of human perception? This is the science behind curveballs, where sports, psychology, and aerodynamics collide in a spectacular dance of deception. And the deeper you go, the more it starts to feel like something out of a science fiction novel. To truly understand the curveball, you have to start with its master illusion, the break. It's not just a matter of the ball curving, it's the way it curves. Pitchers don't just throw the ball and hope it drops. They spin it, fast, and that spin creates a phenomenon known as the Magnus effect. Imagine a ball spinning through the air. One side is rotating with the direction of the airflow, and the other is rotating against it. This creates a pressure differential. The side spinning with the air sees a higher velocity of airflow, reducing pressure, while the other side slows the air down, increasing pressure. This imbalance pushes the ball sideways. It's the same principle that allows soccer players to bend a free kick or tennis players to slice a serve. But in baseball, it's weaponized. A curveball typically spins forward with tight topspin, forcing it to dive downward as it approaches the plate. Depending on the grip, arm angle, and finger pressure, it can also spin slightly to the left or right, creating the illusion that it's snapping sideways. What's fascinating is that the actual path of the ball doesn't curve dramatically, at least not to the level your eyes perceive. Here's where psychology comes crashing into physics like a 95-mile-per-hour fastball. Enter the curveball illusion. In reality, a curveball might only break a few inches compared to a straight pitch. But because your brain is predicting a linear path based on the ball's initial trajectory, when it suddenly drops or moves, it looks far more drastic than it physically is. This trickery of the mind has been confirmed by neuroscientists. In studies using motion tracking and eye tracking equipment, it turns out our brains have a hard time reconciling rapid angular motion with the parallax of a moving object. As the ball transitions from peripheral to central vision, the spin causes our brain to miscalculate the trajectory, leading us to believe the ball breaks more than it really does. It's not just a ball breaking, it's your perception shattering. Now throw in the fact that a hitter has approximately 400 milliseconds, less than half a second, to recognize the pitch, decide whether or not to swing, and then actually complete that swing. That's less time than it takes to blink. During that moment, the brain is operating at Formula One speeds, trying to decode complex spin patterns, anticipate movement, and adjust muscle responses. Professional hitters aren't just reacting, they're predicting. They're using subconscious algorithms built on thousands of repetitions, reading the pitcher's grip, release point, arm speed, and spin axis all in a blink. And yet, even the best hitters in the world get fooled by a good curveball. Because even with all that experience, the science of spin can still short-circuit the brain's predictive model. It's like trying to outthink a mirage. But here's where it gets even weirder. Not all curveballs are created equal. A 12-6 curveball, named for its motion from the 12 o'clock to 6 o'clock position on a clock face, drops almost vertically. It's thrown with topspin, forcing the ball downward as gravity pulls it faster than expected. Then there's the slurve, a curveball slider hybrid that sweeps diagonally across the plate. And don't forget the knuckle curve, where pitchers grip the ball with their knuckles to generate erratic movement. Each variation tweaks the physics slightly, adjusting spin rate, spin axis, and velocity to manipulate both the break and the visual deception. In modern baseball, pitchers now use high-speed cameras and pitch tracking technologies like Rapsodo and TrackMan to dissect these elements down to the millisecond. They can measure spin rate in revolutions per minute, vertical and horizontal break in inches, and even the spin efficiency, a metric that tells you how much of the spin is actually contributing to the ball's movement. The result? Pitchers are now engineers of deception, crafting pitches with surgical precision. But how fast does a curveball spin? Fast. A good major league curveball spins anywhere from 2,000 to 3,000 revolutions per minute. That's faster than the average car engine at highway speeds. And that spin doesn't just make the ball break, it makes it dance. A high spin rate creates sharper, later movement, while a lower spin rate results in a softer, more gradual arc. But here's the twist. Sometimes a slower curveball is more effective precisely because it disrupts the batter's timing and triggers the illusion more strongly. This interplay between velocity and deception is what makes the curveball such a devastating weapon. It's not about throwing the hardest, it's about throwing what the brain can't process fast enough. Now, let's dig even deeper. The seam orientation of a baseball affects how the air flows around it. When a curveball is thrown, the raised seams interact with the boundary layer of air, causing turbulence and further altering the pressure zones. This is why seam-shifted wake, a term you'll hear in cutting-edge baseball science, is gaining attention. It's the idea that the ball's seams can actually push air unevenly in ways that aren't fully explained by traditional Magnus physics. It's the curveball 2.0. Movement that defies what even pitchers intend to do. In fact, many pitchers discover pitches with surprising movement purely by accident during bullpen sessions, only to analyze them with data later and realize the seams were creating unexpected aerodynamic forces. Even stranger, curveballs behave differently depending on atmospheric conditions. A curveball thrown in Denver's high-altitude Coors Field breaks less than the same pitch thrown at sea level in Boston. That's because thinner air at high altitudes reduces air resistance and the Magnus effect. Temperature, humidity, and even wind direction subtly impact a curveball's path. That means the same pitcher, throwing the same pitch in the same way, can produce radically different results depending on where they are. Baseball isn't just played on a diamond, it's played in a constantly shifting laboratory of physics. Let's talk vision for a moment. Hitters aren't just reacting to spin, they're reacting to visual cues so subtle they'd make a poker player jealous. The human eye can track spin up to a certain speed, but at over 80 miles per hour, much of it becomes a blur. What hitters actually see are spin patterns, specifically the red laces of the baseball creating visual cues like a dot or loop. A well-thrown curveball might flash a tight red circle, signaling the sharp drop that's coming. But by the time the brain decodes that pattern, the ball's already moved. Hitters have trained for decades to associate these cues with certain pitches, creating a rapid feedback loop between the eye, brain, and body. It's like playing chess at 90 miles per hour, where each move could strike you out. But perhaps the most mind-blowing part of the curveball isn't the physics or the mechanics, it's the philosophy. Because when you think about it, a curveball is the perfect metaphor for life. It's the unexpected twist. The thing you thought was coming one way, only to suddenly change course. And how we respond, whether we swing wildly or hold back and adjust, says more about our nature than any stat ever could. It's not just a pitch, it's a question. Are you ready for what you didn't see coming? And yet, the science doesn't stop at the plate. Behind the scenes, researchers are still unlocking curveball secrets using computational fluid dynamics, the same tools NASA uses to study airflow over spacecraft. These simulations let scientists visualize the invisible, modeling how every microsecond of spin and airflow alters the ball's trajectory. Some researchers have even created virtual reality batting cages to study how players perceive pitch movement in real time, blending neuroscience, physics, and athletic performance into a unified field of study. Baseball has become a frontier for experimental psychology and motor control research, and the humble curveball sits at the center of it all. And here's a wildcard twist. Curveballs don't just confuse humans, they confuse machines too. In early attempts to train artificial intelligence to recognize pitches, curveballs posed a significant challenge. Because the spin and trajectory deviated from the norm, early models often misclassified them, proof that even advanced machine learning systems struggle with deception rooted in physics and perception. In essence, the curveball is one of the few things in sports that can outsmart both brains and bots. So the next time you watch a pitcher wind up, remember, you're not just witnessing a pitch. You're watching a physics experiment, a psychological con, a dance of spin and illusion that's been studied for over a century and still manages to surprise us. You're watching a legacy that stretches from the sandlots of the 1800s to today's high-tech laboratories. From kids throwing wiffle balls in backyards to MLB stars dissecting spin rates with analytics teams. The curveball has evolved from a backyard trick to a scientific marvel. And yet, its greatest strength is still its mystery. Because the moment it leaves the pitcher's hand, it becomes more than just a ball. It becomes a puzzle, a blur, a question with no time to answer. It becomes the embodiment of everything that makes baseball beautiful and maddening at once. The tension between what you expect and what actually happens. It's proof that in a world governed by laws of motion and mathematics, the human mind and body can still be surprised. The curveball doesn't just break across the plate, it breaks the rules of perception, it humbles hitters, it outwits machines, and it whispers with every spinning revolution that even in a game filled with data, the most powerful force of all is deception. And deception, at its core, is an art form. In baseball, the curveball is the brushstroke, the mound is the canvas, and every pitch is a fleeting masterpiece painted in midair. But here's the final twist. The curveball's effectiveness also lies in what isn't seen. It thrives in the void between pitches, feeding off the contrast. Throw a blazing fastball at 97 miles per hour, then follow it with a looping curve at 78, and watch the hitter's brain glitch like a crashed program. That speed differential is more than just numbers. It's the psychological 1-2 punch that creates timing disruption, the real monster behind missed swings and shattered expectations. Curveballs work best not in isolation, but in orchestration, sequenced like notes in a symphony of misdirection. And in this symphony, the pitcher is both composer and conductor. Think of Clayton Kershaw, whose iconic 12-6 curveball has buckled the knees of countless batters. Or Barry Zito in his prime, fooling MVPs with pitches that look like they were shot from a rooftop and dropped off a cliff. These aren't just athletes, they're illusionists. And like all great magic, the key isn't in what you see. It's in what you think you see. Because even after over a century of curveballs, with all our high-speed cameras and supercomputers and VR headsets, we're still chasing the secret of that drop, that swerve, that impossible break. And maybe that's the point. Maybe the curveball endures precisely because it dances at the edge of what we can know. It reminds us that not everything in the game, or life, can be predicted, measured, or mastered. That sometimes, the unexpected is the point. And when that ball dips out of the sky and makes a fool out of even the most seasoned hitter, we're reminded of something deeply human, that in the battle between knowledge and instinct, mystery still has a place. That the brain, for all its brilliance, can still be beautifully wrong. And maybe, just maybe, that's why we watch. Because in every curveball lies the thrill of not knowing what comes next.